G'day, welcome to our final little part of our uniform circular motion discussion. So we're just going to talk about today some of the forces that will cause uniform circular motion. So just want to start with what we finished with last time, and we talked about the centripetal acceleration is equal to v squared on r. Okay, and remember that the centripetal acceleration is radially inwards, and from that we can actually derive a force for the centripetal force from Newton's second law. So if you remember Newton's second law, F equals ma, right? And in this particular case, the acceleration is the centripetal acceleration. So we can just put a little subscript c, and then substitute in the v squared on r, and we have an expression for the centripetal force, mv squared on r. Again, what's the direction? Radially inwards. Okay, same as the acceleration. Okay, and on the board there I've got some examples of the different forces that can cause uniform circular motion. So firstly there is the tension force. So the tension force is simply if you've got a ball tied to a piece of string and you're twirling the ball around your head so that the ball's going in a circle, then it's the string, okay, the tension in the string that's pulling the ball inwards. It's supplying that centripetal force inwards, radially inwards, and then the ball will continue to go around in the circle. So that's the first one there, the tension force. The second one there is the friction force. So imagine a flat road and a car is going around a bend, okay, around a bend on a flat road. How is the car going to actually negotiate that turn? Because we know from Newton's first law that an object in motion will continue in motion unless acted on by an external unbalanced force. So what is the force here that's causing it to go around in a circle? Well, it's actually the friction between the tyres and the road. And the friction acts in such a way to pull the car inwards towards the centre of the bend. So the bend will have a certain radius, and the force of friction is actually going to be pushing inwards, again radially inwards, supplying the centripetal force. Okay, the third example there is gravity. So we know that gravity is a mutual force equal to the gravitational constant multiplied by the product of the two masses divided by their distance of separation squared. So this is the force that you would find for a satellite going orbit around the Earth. Okay, it's going in a circular orbit. What's pulling it inwards? It's the force of gravity. Now gravity is acting downwards, but in this particular case, because it's going in an orbit, it's actually also radially inwards. So the downward force matches the radially inwards force. Okay, and we can also equate that with the centripetal force. Okay, mv squared on r, and if you kind of cancel all that down, you'll find actually an expression for the speed of a satellite. Okay, if you want a satellite to stay in orbit at a particular height, a particular radius, then it needs to have a particular speed. All right. And that speed is given by the square root of gm on r, where g is the gravitational constant, m is the mass of the central object, in this case it might be the Earth, and r is the radius of orbit of the satellite, which of course includes the height of the satellite plus the radius of the Earth. Okay. The fourth force there is the electric force. So this might be the force, say, between a proton and an electron. So the electron's whizzing around the nucleus of an atom, and what force is causing it to stay in that orbit? It's the electric force, which we can actually find from Coulomb's law. So also an inverse square law like gravity, but it's found by multiplying the product of the two charges, the nucleus, the positively charged nucleus, and the charge of an electron, say, multiplied by the electrostatic constant divided by the radius squared. Okay. The fifth one there is the magnetic force, and so if a charge has to be a charged particle, has a velocity as it enters into a magnetic field, like that, so it might be a proton, for example, is coming into a magnetic field, it will actually experience a force due to the magnetic field which is actually at right angles to its motion. Right there. But of course, as its motion changes direction because of that force, the direction of the force also changes. And the force is always directed, guess what? Radially inwards. So it's actually a centripetal force as well. Magnetic force can be calculated by multiplying the charge by the velocity and the strength of the magnetic field. We can equate that to the centripetal force formula, this one here, mv squared on r. We'll actually get an expression for the radius of orbit as the charged particle moves within that magnetic field. The last one I want to talk about today is the banking of curves. So you can imagine perhaps in a country road where as you are coming down the bend of a steep hilly road, for example, you sometimes notice that the road is kind of tilted slightly towards the centre of the bend. And that's no accident, okay? That tilting of the road actually helps the car to move in a circular motion around the bend. And if we look at this carefully, we can actually get an expression for how fast a car can go safely around a bend like that. Alright, so I've got my little sketch there with my little pink vehicles, and you can see cars coming around a bend, and the bend is tilted at angle theta, like that, and that tilt in the bend is actually going to supply a force which is going to push the car around the bend. It's actually going to provide two forces. Essentially, the road is actually pushing up on the vehicle, supplying what we call a normal force. A normal force is at right angles to the surface of the road. Okay, so the normal force is at right angles, and that's pushing kind of at an angle, depending on the tilt of the road, is pushing up at an angle at 90 degrees. From that force, we can see that it does two things. Firstly, it will stop the car from falling further downwards. So there's a force, a component of the normal force going directly upwards. We might call that the vertical component. And then there's a component of the normal force that's going horizontally. And we might call that FH. Now, if the car is going at the right speed, then the weight of the vehicle, which is directly downwards, can be found by multiplying the mass of the car by the acceleration due to gravity, is directly counterbalanced by the vertical component of the normal force. So these two forces are actually in balance, if you like. The horizontal component of the normal force is actually the one supplying the centripetal force to keep the car going around the bend. So what we can do is actually get some expressions from these two once we redraw the triangle and see if we can see what the components equal. So if you look carefully at this diagram, you'll hopefully be able to see that angle theta there actually corresponds to the top angle in the triangle. Okay, so this is angle theta here. So this one is angle theta as well. This one is 90 minus theta, and therefore we've got theta in the top corner of the triangle. From there, we can actually get an expression for the normal force in terms of angle theta. So, the vertical component of the normal force is equal to Fn, the normal force, times by cos theta, and the horizontal component is Fn multiplied by sine theta. Now, we know, however, that the vertical component is balanced by gravity. The magnitude of those two forces are equal. Fn cos theta equals mg. And the horizontal component is the one supplying the centripetal force. So Fn sine theta has to equal mv squared on r. We've got two expressions, and we can do a little bit of mathematical trickery, if you like. If I call the top one expression 1 and the bottom one expression 2, what I'm going to do is I'm going to divide those two expressions by each other. So I'm going to divide the two equations. I'm going to divide equation 1 into equation 2. So Fn sine theta equals mv squared on r divided by Fn cos theta equals mg. And as long as I do the same thing on both sides, I divide both sides by each other, the equality should remain. So Fn's cancel, and the masses cancel, and you're left with a very neat expression which connects the speed, the acceleration due to gravity, and the radius of curvature, and the angle of the bank. Is known as the banking angle formula. So I'll just explain it one more time. This expression connects the steepness of the bank in the curve to the speed of the vehicle in this case, and the radius of curvature plus gravity. So this is kind of like the ideal speed that you need to go to travel around that particular curve without relying on the friction force. Okay? You can get all of your centripetal force from the horizontal component of the force coming from the road, or the normal force. Okay, so that's it. Thank you.